Welcome to our video on polars, our first day of polars. We got a couple of these coming up. So understand that in pre-calculus, we probably to become perfect experts on polar. So we're going to do that now. And add some calculus in it. So for polar, I really want to make this as simple as possible. So polar coordinates are just a different way to graph something representing only the radius at a particular point and the theta value at a particular point. Okay. So this entire box right here is stuff that you should have known from pre-calculus. Okay. So converting coordinates. So by the way, we use radius and theta to represent polar coordinates. Let's see here if I can kind of find. So here's a graph, and we'll get to this one. So this is what polar coordinate graph looks like. Okay. So this is not like an XY graph whatsoever. It represents some type of curvy. We usually use trig in here. It's the whole reason of the polar coordinates. You'll see that when we get to the conversions. But we just graph off of this little circular thing. So like at pi over 3, what's the radius? If the radius is positive, it's over here for pi over 3. If the radius is negative, it's actually on the other side of pi over 3. Okay, so that's just what a polar graph looks like. So now converting it, this is like the big old important part. You need to know how have all this stuff memorized. X is equal to r cosine theta. Y is equal to r sine theta. This is the equation of a circle, by the way. So r squared equals x squared plus y squared. And then if you were to actually solve for x and y, not solve for it, but if you actually were to divide these two things, so y divided by x, you would get tangent of theta. So kind of be aware of that. So these two things really are the driving force into here as well. We have to be able to convert equations. We'll do that from rectangular to polar, vice versa, and we'll be able to graph those. All these different types of graphs here: circles, lemnicons, cardioids, roses, and I cannot say this at all. Lemniscates. I probably said that wrong. And they're all down here. I don't think they're labeled though, but this one is. So cardioid looks like a heart. Lemnicon has a little circle in it. Those are really the big ones. A circle, you know what a circle is. And then a rose, they're over here when we have like these petals and stuff like that. And that's really all that we focus on. So with that being said, let's go ahead and be able to find the rate of change of this stuff. So using these formulas, x is equal to r cosine x and y is equal to r sine x. To find dr dx, it's going to be dy d theta over dx d theta, just like what we did for the parametrics, but this time instead of it being with respect to time, it's with respect to theta. So when we do this, unfortunately, it's going to bring out some implicit differentiation because we have two different variables. We have an r and we have a theta. So this is what it's going to actually look like here. So the top, I'll do this in magenta. So the top we get here when we do our product rule is going to be dr d theta sine theta plus r cosine theta. D theta, we're not going to write that down. And then dx d theta is going to be dr d theta cosine of theta plus r, derivative of cosine is negative, so I'm actually make that a minus sign, so minus r sine theta. Okay, so you can memorize this or just understand how the heck it works. So this is a formula that we need to know for rate of change for polar coordinates. It's not the easiest thing to memorize. That's why I prefer you just to understand what the heck is going on. We're taking the derivative of y with respect to theta divided by derivative of x with respect to theta, which requires a little bit of implicit because I have a y variable, an r variable, and a theta variable doing everything with respect to theta. Okay. And then arc length, nice little fun formula here is the length is the integral from, this is alpha to beta because those represent angle measures of r squared plus dr d theta all squared d theta. All right, so with that, let's go ahead and go through some of these problems here. Very, very basic one-step, two-step problems, nothing totally crazy, but you can see we got a lot of things going on here just to make us a bit more familiar with polar coordinates. So Find the rectangular coordinates given this right here. So I have, this is r, so r is 7, and theta is equal to 2 pi over 3. So since x is, I'm not going to rewrite it again, but x is r cosine theta, it's going to be 7 cosine of theta, which is 2 pi over 3. All right, and that's going to give us cosine 2 pi over 3. That is in the second quadrant, 3, so it's 1/2, so it's negative 1/2. So I'm going to get 7 times negative 1/2, which is negative 7/2. For y, we're going to get r sine theta, so it's going to be 7 sine of 2 pi over 3. 2 pi over 3 is in the second quadrant, so it's going to stay positive. It's going to be 7 times root 3 over 2, so this is going to give me 7 root 3 over 2. So rectangular coordinates are going to be negative 7/2, 7 root 3 over 2. If I were to plot this, I'll just kind of show you over here. If I were to plot this point, it would be over here. So using this graph, here's the origin. So we're going to go out in the 2 pi over 3, out 7, 1, 2, 3, 4, 5, 6, 7. So it's like over here, which makes sense because I would make this into an x and y equation. It would be to the left, which is why it's negative, and then it's up, which is why it's positive. So it all makes sense. Okay, polar coordinates. So now we got to use these two equations here to go from from rectangular to polar. So to find r squared, so r, we get to use this equation for r squared. So we're going to get r squared equals 3 squared plus 4 squared. That's a Pythagorean triple, so r is going to equal 5. And then we got to use the tangent one right here. So tangent of theta is equal to y over x, which is 4 over 3. So if we were to do a little bit of magical calculator work, we just do inverse tangent 4 over 3. It's in the first quadrant. I'm going to get a positive value of 0.927. So my coordinates in polars are 5, 0.927. And this is just to familiarize yourself a little bit with what's going on with polar. Okay, so again, if I have a graph, if I have like 3, 4, it's probably somewhere over here-ish. So you go out 5, 1, 2, 3, 4, 5, and then 0.927. What is that close to? That's close to like pi over 3-ish, a little less than that. So it's probably like out here-ish, which makes sense. Okay. Do I want to do the graphing now? I'll do the graphing later. I'm going to tackle these two, and then I'll hit the graphing, and then I'll hit the calculus. All right, so find the rectangular coordinates for this. I'm giving you r. I need to change everything into x's and y's. Okay, so what I'm first going to do here is, before I change r, I want to change this into sines and cosines for the secant, tangent. It's just much easier that way. And then we deal with r at the end, because sometimes there's a trick that we can do with the r's if it's once in terms of sine and cosine. So secant is going to give me a 1 over cosine. Tangent gives me a sine over cosine. So I'm going to end up getting r to equal sine theta over cosine squared theta. All right, and then I'm going to multiply both sides by cosine squared. And maybe you'll see what's going on here. So I'm going to get r times cosine squared theta equals sine theta. Now I need to make this look like one of my formulas here. So I need it to look like this and or that right here. And I'm super close because I have an r here, but I have a cosine squared. So it doesn't match up quite yet. And over here, I'm missing an r. So I'm missing an r here to match up with the squared. I'm missing an r on the right side to match up with the squared. So let's just multiply both sides by r. And that's going to give me, in red, r squared cosine squared theta equals r sine theta. Well, r sine theta is the easiest one. R sine theta is going to be y. R squared cosine squared isn't the same thing as r cosine all squared. So r cosine is x, so it's going to be x squared. So this is a lovely parabola. Couldn't tell just by looking at it, but that is a parabola. So all we have to do here is just completely transfer into x's and y's. Let's do the complete opposite. So let's transfer everything into polar, which I think is actually the easier one to do because you can just straight up just plug in the formulas. You don't need to overthink this one. I'll do this one in green. So all we're going to do is just replace that x with, right up here, r cosine theta. We're going to replace the y with r sine theta. So we're going to get 9 r cosine theta times y, which is r sine theta. And that equals 4. That's really like good enough right there, but I'll make it look nice and clean. Usually we have this with like r equals, some type of r equals. So we're going to get 9r squared cosine theta sine theta equals 4. And let's just solve in terms of r squared here. So I'm going to divide the 9 to both sides and the cosine sine to both sides. So I'm going to get r squared equal 4 over 9 cosine theta sine theta. And it doesn't look very pretty, so I'm just going to change this to 4/9. Since cosine's on the bottom and sine's on the bottom, I can change that into secant, cosecant, respectively. And there we go. All right, so some basic polar stuff, pre-calculus type of deal. We'll do one more that's a little bit of pre-calculus, and then we'll get to the calculus of it by finding arc length and by finding what is this, slope. Okay, so for graphing, hopefully remember how to graph from back in the day of sine and cosine stuff. So I'm going to do, this is going to be 3 plus 3 sine of theta. So I'm going to real quick give this a little sketchy poo here of a sine function, just basic sine. So I'm just going to just do pi over 2, pi, 3 pi over 2, and then 2 pi. And I'm going to sketch this in rectangular coordinates. I'm going to transfer it over here. Okay, so I have an amplitude of 3. So an amplitude of 3, and then I'm actually shifting sine up 3. So if I usually start sine at 0, so I'm actually going up to 3. And my amplitude is 3, which means I'm going to go up 3, down 3. So I'm going to go up to 6, and then down to 0. It's important to know how far down it goes as well, because if it goes below, that's going to really change up my graph here. But it actually ends up at 0. So I'm going to start here, 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 and here. And here's our basic sine graph. Okay, so what I'm going to do is take these points and plot them over here. So at 0, this is 0, I'm at 3. So 1, 2, 3. At pi over 2, I'm at 6. So that's 1, 2, 3, 4, 5, 6. Okay, so again, each one of these little spaces is the radius. At pi, I'm going to be at 3. So I got to go in the pi direction. 1, 2, 3. At 3 pi over 2, I'm actually at 0. And then at 2 pi, I'm back at 3, which I'm already there. Okay, so this does not make a triangle. Okay, so we're going to kind of follow this path right here. So if you notice, we're staying positive and we're increasing until we get to pi over 2. So you're going to go cross a couple of these radiuses right here. So we're increasing like that. And then here we're decreasing down to 3. So we're going to go make it look like this. Okay. And then we're still positive until we get to 3 pi over 2, which happens to be 0. So we're not going to just draw a straight line. I'm actually just going to continue this until I get to 0. So if you notice, I'm decreasing the lines right there. Okay. And then I'm going to increase till I get back to pi over 2. So I'm going to increase as I get closer and closer to pi over 2. So that is a cardioid because it looks like a heart. Okay, so that is how you graph, just reminding you how to graph those. All right, let's go ahead and tackle a little bit of calculus for these problems. All right, let's go ahead and find the length of the arc. This is super nice because it straight up just tells us how to do all this. Gives us the theta, gives us the r Super nice, right? Because our formula is right here. If you don't mind, I'm going to cover everything else up except for this. There we go. So here's our formula here. So I have my two angle measures, so it's going to go from 0 to 2 pi square root of r squared, which I have that, square it, plus dr d theta squared. So I'm going to take the derivative of this with respect to theta. It's not a big deal. A little bit of side work here. So dr d theta is going to equal, well, derivative of 2 is nothing. And then negative 2 cosine, that's going to turn into a positive 2 sine. So I'm going to get 2 sine theta. So dr is 2 sine theta, and that's going to be all squared d theta. So this is going to be the length of this function right here. So essentially, I know it's not this one we're finding. I'm aware of that. We're trying to find how long this brown graph is, how long it is. All right, obviously, it's not the same graph, but that's kind of what I'm trying to get at. How long is the graph here? And then from here, this is your setup. So let's go ahead and find the length. This would be a calculator problem, mind you. So go ahead and grab my handy-dandy calculator. And literally just type this in. And I can't have theta, so I have to use x's instead. So pull up your integral 0 to 2 pi of the square root of 2 minus 2 cosine theta. I can't do that, so I have to use x. And that is all being squared. Just be careful with your parentheses. That's good. Plus 2 sine theta, which is just x, and that's all going to be squared, and that is going to be dx. So we need an answer of, wow, that was very clean. 16. That was very clean. I didn't even have that answer in my notes. Okay. Hey, last one here is we're going to find dy dx. So that formula that we have to use, which is going to be right there. We use the formula of the graph. And then we're going to plug in a pi over 6. Okay. So here we go. So first off, what's dr d theta? Because I'm going to need to plug that in. So dr d theta is going to be 2 cosine theta. That's important. So as we do this, for dy over dx, the numerator is going to be dr d theta, which is 2 cosine theta times sine theta, plus r, which is that right there, 3 plus 2 sine theta, times cosine theta. All over dr d theta, which again is my 2 cosine theta times cosine theta, plus, minus, turn it to be negative anyway, so minus r, which is 3 plus 2 sine theta, times sine theta. And literally all we're doing here is we're just going to plug in a pi over 6. You can simplify this a little bit if you want to. I'm just a little bit short on time here in this video. All we're going to do is just plug in a pi over 6. For theta, plug it in there. It is a little bit of work. I totally get that. I would probably simplify a little bit just to make your life a little bit easier. But I'll just tell you it's negative 5 root 3. So that means that, again, I'll just come back to like this graph right here. At pi over 6, the radius is changing at a rate of negative 5 root 3. Now, obviously, it's not the same graph. Okay, let's get that. It's not the same graph. So in this case, for this graph, we're actually decreasing the radius for this. So I know that's a lot of information just threw at you with day 1 polars here, but it starts to slow up a little bit with day 2 and day 3. So that is our video.